All right, so in last video we started off with learning some basic definitions that we use in when talking about sequences, general terms, terms. We learned a little bit about the notation using subscripts. A much harder question, a much harder question than if I give you the general term and ask you to find me the first five terms. That's pretty easy. A much harder question is, well, what if I just give you a set of terms? Can you find the general term? Right? So you notice the difference between the prior questions and the one being asked of you right now. So can you actually find the general term? This this is a little bit harder to teach, but the good news is we have a couple of very handy tools, as long as we can establish a few things. But for the most part, if you're pretty good at spotting patterns, you will be able to find the general terms of sequences easier than others. But the goal of this section is not to teach you to teach you pattern seeking abilities and things like this. But what we're really focusing on is what are the types of sequences that we can run into. And the first type of sequence I want to discuss is what we call an arithmetic sequence. Okay, so an arithmetic. So now an arithmetic sequence it's pretty easy to recognize. So let's start with this very first term, 3. So somehow, because we don't know the general term, we don't know the rule, but somehow we can go from a 3 to a 7, and then from a 7 to an 11, and then from an 11 to a 15, and so forth. Now, if we were told that this sequence is arithmetic, then that would mean that there is what we call a common difference between each term. Okay, now we normally use D to denote common difference. And really, let me not lose you here. It just means that if it's arithmetic, if the sequence is arithmetic, then whatever I add to 3 in order to get to 7, I must add that same number to have gotten to 11, to 15, to 19. So that's what we mean by a common difference. It's the number that you combine, the number that you add or subtract to move from term to term. So the way that you could calculate what the common difference is just to take, let's say, a sub n plus 1 minus a sub n. So in other words, if we take the 7 minus the 3, what do we get? We get 4. If we take 11 minus 7, we get 4. If we take 15 minus 11, we get 4. So this is the way that you would find the common difference. Okay? Now, again, that's assuming that we are told it's arithmetic. Now, if we're not told up front that it's arithmetic, then we have to go in there and investigate a little bit more. But the idea is, if we know that it's arithmetic, then we know that there's a common difference, and I just got done showing you how to find the common difference. Now, so I think you're with me so far that the common difference is not that bad to find. Let's go ahead and establish that we still have not answered the question. The question is, what is the general term? And now, let me go ahead and write one more little handy tool that you should write down. So again, since we're discussing arithmetic sequences, all arithmetic sequences, the general term can be written as the first term plus, now this is going to be n minus 1 multiplied by the common difference. All right, so notice that the only thing you need is you're going to need to know what D is, and you're going to need to know what A sub 1 is. With those two things, the first term and the common difference, you can get the general term. Do you agree with me so far? Do you understand what I'm saying? Well, let's go ahead and do this. So A sub 1 for part A is 3. Right? That is the very first term of our sequence. The common difference D is 7 minus 3 or 11 minus 7. Either one is 4. So with those two things, with those two values, I'm going to plug the 3 in for A sub 1, and I'm going to plug the 4 in for D, and then we got it. We got what we were looking for. So A sub n is equal to 3 plus n minus 1 multiplied by 4. Now, normally that is fine to keep your general term in that setup. Normally, you would distribute the 4 and combine. So you would normally see it written as 4n minus 1 as your general term. Now, of course, the good news is you can now go in and start checking things. So if you I'm going to hold my cursor here. So if I plug a 1 in for this general term, actually, I'll tell you what, I'll hold my cursor here so you can see it a little bit better. If I plug a 1 in for that general term, 4 times 1 is 4, minus 1 is 3. If I plug a 2 into that general term, what do we get? Well, 2 times 4 is 8. 8 minus 1 is 7. So you see how we could continue in this fashion, but that is the way we find the general terms. Again, if it's an arithmetic sequence. So let's start this next problem by saying, well, okay, well, this time we're not told it's arithmetic. That doesn't mean that it's not. It's just that we're not told up front that it is an arithmetic sequence. So how do we start to investigate? Well, you can see how this would be your first term and second term and third term and so forth. So maybe we just start with a little bit of investigation. Maybe this is some scrap work off to the side. A sub 2 minus A sub 1, what does that give us? Well, that would be 2 minus 5 is negative 3. And then we would have A sub 3 minus A sub 2 and figure out what does that give us. Well, that would be negative 3. No, I'm sorry, my apologies. A sub 2 minus A sub 1 is negative 3. Yep, so let me plug in my numbers before I start saying silly things. So, oh, I know why this is, I know why this is going to, I just paused for a second because I wrote this down incorrectly. I thought I made an arithmetic mistake, but I didn't write an arithmetic mistake. I actually wrote a mistake when I was writing the sequence. Okay. So ready? So A sub 2 minus A sub 1, yeah, that makes sense. That is negative 3. Now we would have A sub 3 minus A sub 2. Negative 1 minus 2, that's also negative 3. Now let's see how it's making a little bit more sense. A sub 4 minus A sub 3, and so forth. So negative 4 minus negative 1, so plus 1, so E is also equal to negative 3. So, okay, well, I get that that's not exhaustive, but we have, for right now, we have enough to make a, let's just say we have enough to determine that this is an arithmetic an arithmetic sequence. We really didn't roll up our sleeves very much. We only tried it for the first three, and but nevertheless, if it is arithmetic, then the general term should be able to be written if we have the first term and we have the common difference. Okay, so let's go ahead and establish that the common difference in this case is -3. And the first term of our sequence in this case is 5. All right, so let me go ahead and plug in some numbers here. So a sub n is going to be equal to 5 plus n minus 1 multiplied by -3. And again, normally they would go ahead and combine like terms and distribute so that you could rewrite it as a sub n is equal to, what would that be? -3n plus 8. There is your rule, there is your mapping, there is your general term for your sequence. Now, at this stage, you would start to test it a little bit and see if, plug in a 1 and see if you get a 5. Plug in a 2, see if you get a 2. And then that will give you a good feel that if you've done everything correctly. All right, now, so let's say, again, just like we jump in to, just like we jumped into part B, let's say we jump right in to part C. And we start doing a little bit of testing, right? So we take a sub 2 minus a sub 1. So that would be 6 minus 2. And we get 4. Then we take a sub 3 minus a sub 2. That would be 18 minus 6, which is 12. Wait a minute. So right now, we have enough to determine that this is not arithmetic. Now, that doesn't mean that we still can't find the general term. It just means that we cannot use the rules for finding the general term for arithmetic sequences if the sequence itself is not arithmetic. Okay? So I'm going to leave this open for just a second. I'm going to kind of scroll to the next page and talk about another type of sequence that we're going to be interested in. So we just talked about arithmetic sequences, and now let's talk a little bit about geometric sequences. And then we're going to go back to the previous page and answer that question. All right, so a geometric sequence. So recall, arithmetic sequences differ by that common difference. You add 3 every time, or subtract 3 every time. Geometric sequences differ, right? They differ in term, right? By what we call a common ratio. Okay, so not a common difference. You don't add the same thing to go from every time to go from term to term. Instead, you have a common ratio, R. So let me just make up a geometric sequence. Let me show you how you could think about calculating R. And then we'll go back and we'll go ahead and give you the trick. Okay, so let's assume that your sequence is 100, 50, 25, 12 and a half, etc. All right. So this is a geometric sequence, and you can see that it appears that we're just cutting the previous term in half every time, right? So let me show you how you could think about that. Because remember, what we're doing right now is trying to figure out how would you find R. Well, if we start with 100, you could think about the next term would be 100 multiplied by a half. The term that follows that would be 100 multiplied by a half squared, right? Stay with me just a second. So half of 100 is 50. We know that. Half of 50 is 25. We know that. A fourth of 100 is also 25. So you can see how you can write 1/2 squared is just 1/4. And 1/4 of 100 is also 25. And are you starting to see how you can think of it as we continue? This would be 100 times a half to the power of 3. So this half that's showing up, okay, the half that's showing up in each of these problems is the common ratio. So that means that any geometric sequence can be written as a sub 1, right? That's 100. That's the first term, and you notice that 100 showed up each time, multiplied by R. Now, R is the 1/2 that you're cutting everything in, by a half, to the power of n minus 1. All right. So let's talk a little bit more about the R, and then we're going to go back and answer that question. So the common ratio R. So first let me say that there are some stipulations. R cannot equal 1, okay, and still have a geometric sequence, right? 1 squared, 1 cubed, 1 to the power of 4. That doesn't make any sense. R also cannot equal 0, right? So there's a few stipulations on what the common ratio can be, but aside from that, if you were trying to find the common ratio, what you can do is you can take the second term and divide it by the first term. Or more generally speaking, you can take the preceding term, which is n plus 1, and divide it by the previous term, which is a sub n. So does it make sense to you that if you, let me just go ahead and show you what I'm talking about here. So a sub 2 divided by a sub 1. So 50 over 100 is a half. Or 25 over 50 is a half. So this right here, where you're taking the current term divided by the preceding term, is the way that you can actually calculate R. So R equals. All right, so as of right now, I'm going to grab my definition of R and my definition of a geometric term, nth term, and let me come back over here and answer this question. Ready? So it's possible that this is geometric. It may, I mean, we'll test in just a second. But we found that R, if it was geometric, would be a sub n plus 1, right, divided by a sub n. And we found that the nth term or general term of a geometric sequence is just a sub 1, the first term, multiplied by r to the power of n plus, minus 1. Okay. So let's go ahead and see if we can figure out if this is geometric. So if we took 6 divided by 2, or 18 divided by 6, do you see that what's happening is you're getting 3 every time? 54 divided by 18. In other words, it's not that what's happening here is as you go from term to term, you're just tripling the previous term, right? 2 times 3 is 6. 6 times 3 is 18. 18 times 3. So in this case, your R value is equal to positive 3. Now, as long as I have the common ratio, which I do, and the first term, which is 2, I can answer this question of what is a sub n. So the general term of this sequence is going to be 2 times 3 to the power of n minus 1. And at this stage, you could go through and you can test just to make sure that you're producing the terms of the sequence. But that's the idea. That's the idea of general terms and how to find general terms for arithmetic sequences and geometric sequences. Now, the idea of where we want to be able to go with this and how it ties into the study of calculus can be found with just our old friend, the limit. So one of the things that we're interested in, or going to be interested in very soon, is questions like, hey, even if the sequence goes on forever, even if it is an infinite sequence, does it add up to a finite number? Or does it just continue to go to infinity? So, and to kind of start to build on what we would need to answer questions like that, we're going to ask questions about whether the sequence itself converges, right, or diverges. So, in scenarios like the previous examples, the first two were arithmetic, and I'll go ahead and tell you that all arithmetic sequences, right? So, for example, let's take a look at part A on the previous page. Part A was, let's see, what is it? It was, actually, let's take part, let's take part A. So 4n minus 1. So that's part A from the previous page. So that's an arithmetic sequence. A sub n is equal to. Now all arithmetic sequences are going to diverge. And the way you can think about it is as you let n approach infinity, right? You keep choosing larger and larger values of n. Arithmetic sequences are never going to converge on a single number L, right? Unlike what we have here. So they're going to just continue to grow. It's just every time you choose a larger n, you're going to get a larger a sub n. And they're going to, in that fashion, they're just going to continue to grow and they're going to diverge. Okay? There was a very popular videos on a YouTube series called Numberphile, where they were using some they're using some techniques for series and applying it to questions like I don't know how much I want to go into this, but they're applying it to questions about the sum of all natural numbers, which is a very old series from a mathematician by the name of Ramanujan, to arrive at this oddity, right? Where if you add up 1 plus 2 plus 3 plus 4 plus 5 forever, you get to negative 1/12. Right? It's a very, very interesting video. At first, I was actually very angry that with the treatment and some of the terminology that they were using when they were talking about sums, which the Ramanujan knew what he was doing and what he was working with when he was working with the zeta functions, and the idea is that the word sum has the meaning of the word sum in the cases that Ramanujan, or in this type of case, has no parallel to the way we normally use the word sum. So it's very tricky sleight of hand techniques that they were doing in the video. But believe it or not, it got 1 million hits. Everyone was running around telling each other that, hey, guess what? If you add up all the natural numbers, you get a negative number. So I later changed my opinion, and one of my colleagues convinced me that, hey, do you realize we have 1 million people who are in the world of mathematics who are now discussing topics that very few people in the public ever talk about. So it is true. So it did bring even though they were a little bit informal, they did spark some interest in a very cool topic. So I'm actually very happy they made the video. Now, if you have no idea what I'm talking about, then you were just daydreaming the last few minutes, and that's okay. You just need to come back to me now. So arithmetic sequences always diverge. Now, what about geometric sequences? Geometric sequences are a little bit more interesting. Do they diverge, or do they converge upon a number? So that is something we're going to talk a little bit more about. So instead of me going into like the epsilon definition of how things converge and diverge, the geometry can tell you quite a lot about what we mean by convergence. And I think it would be better to just show you what I'm talking about. Okay? So let me go ahead and restate something I said in a previous lecture, that you can think about sequences as functions, right? Remember me making that statement that sequences can be thought of as functions, because it's just a rule to tell you how to go from term to term. But because of that, we can use the same properties of limits that we used when we were discussing functions, only now we'll be using them to discuss sequences. So I think I'll try to write a one sentence description on what is really we're going to be doing for the rest of this section. So what we're going to say is a sequence fails to have a limit when the terms of that sequence just increase or decrease without bound. Without bound. Right? So here, if you have some sequence of terms, if those terms just keep increasing and increasing and increasing without bound, meaning they never start to approach some L, then if the sequence does not have a limit, then that's really what's happening. The terms are just increasing, 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 or decreasing without bound. So example 2. So example 2 asks the following question. It says, find the limit of the sequence whose nth term is as follows. Now I'll write that a little bit larger. So we have a sub n is equal to 1 plus 1 over n to the power of n. All right, and now to talk about the limit of the sequence, what we're really discussing is, okay, as you let n grow to infinity, right? As the limit as n approaches infinity of what? Of a sub n. Now, for this question and this only question, I'm going to show you I'm going to show you like a window of how this is very exactly the way we used limits when we were approaching functions. So this would be the same thing as if we were talking about f of x is equal to 1 plus 1 over x to the power of x, right? So I've written the same, two different ways of writing the exact same expression, right? The exact same rule. And okay, well, if we were talking about the limit notation for functions, this would be the limit as x approaches infinity of f of x. Okay, so I write these two things side by side because this is information you have seen before. This is the same techniques applied to a different notation. And now let's go ahead and continue. Well, back in chapter 5, I'm working on the right side here. Back in chapter 5, I've already shown you that the limit as x approaches infinity of 1 plus 1 over x to the power of x is actually equal to the constant e. Okay? So that means, in the same sense, that the limit as n approaches infinity of the general term a sub n must also be equal to the constant e. So does the limit fail to exist for example 2? No, the limit is e. That means that our sequence converges. Okay, converges into e. All right, you would notice this if you just, I'm not going to do this, but if you just started writing the terms, as you continue to write out these terms, you would see that the next term in that sequence is going to start to look a more and more like the constant e. All right. Now, example 3, we're asked to do the same thing. We're asked to take a look at some of the general terms that we were given. I think this was back in a previous example. And we want to be able to make a statement as to whether it diverges or converges. Does the limit exist? So we want to make a statement. Does it diverge or converge? Or does the limit exist? Right? Does the limit as n goes to infinity, does it exist? All right, well, let's look at the first one, right? This was a previous example. So here's your sequence. It's 2, 4, 2, 4. And now the general term that produced those was a sub n is equal to 3 plus -1 to the power of n. Now, I'm going to answer this question two different ways. First off, remember when limits fail to exist? Limits fail to exist, one, when it's not approaching the same number L from both sides, right, as you approach C from both sides of C. Another way is unbounded behavior, right? If this continues to go to positive infinity or negative infinity, we would say the limit fails to exist. The third way that a limit fails to exist is when you have this oscillating behavior, right? Notice that this term is oscillating back and forth, 2, 4, 2, 4, 2, 4, 2, 4. It's oscillating back and forth. So that we would say that limit fails to exist. Now, the other way is to simply think about it as, well, if we were talking about the limit as n approaches infinity of 3 plus -1 to the power of n, you can now see that this, for all our purposes, is the same as saying 3, what? This is, you can think of it as 3 plus -1 to the power of infinity. Well, that is an indeterminate form. You don't get to just take a number and raise it to the power of infinity and start applying algebraic techniques and things like that to the infinity. So either way, what we would find is this, because there is this oscillating behavior, because the terms alternate between 2 and 4, and we are going to be able to make the statement that the limit fails to exist. Therefore, we would say that this diverges, right? It does not converge onto L. So this diverges. All right, well, let's take a look at part B. So again, I believe this was from a previous question, I believe, but either way, let's take a look at the limit as n approaches infinity of n over 1 minus 2n. All right, well, what do we got? Well, direct substitution. What does direct substitution give us? Well, direct substitution would give us an indeterminate form of infinity over infinity. In Calc 1, the way we would have got around this would be to divide, right? We would use some algebraic manipulation here. So we would say the limit as n goes to infinity of, let's divide the top and the bottom of that fraction by n. 1 over n minus 2n over n. All right, so that is really the limit as n approaches infinity. And let's see what's left. So n divided by n is 1. 1 divided by n, we'll leave that. And then 2n divided by n is minus 2. Okay, so now you remember what happens here. If you start dividing something up an infinite amount of ways, then that just goes to 0. So we end up with 1 over 0 minus 2, or -1/2. So that -1/2 lets you and I agree that the limit does exist. Okay? So if the limit exists, then we are not able to rule out the divergence, right? It doesn't. If so, as I was pointing out over here, we get to, sorry, wrong page. So the idea that if the limit L of a sequence exists, then we get to make the statement that the sequence converges, right? It converges to L. So here, the limit existed. So this sequence converges. Okay, converges to -1/2. All right. I think that's enough for a video. Trying to make these a little bit shorter so you can watch them in parts. But when we get back, we'll do the very last section for our last part of this first section. See you in just a bit.